Hi, I'm Suraj Reddy,
I'm Leo-san.
And I'm Avi Narula.
and we worked on Poolbot, a physics-aware mobile manipulator for multi-shot autonomous billiards. We wanted to see if a robot could play pool, a task that we believe is a compact benchmark for precise contact, long horizon planning, and mobile manipulation. Our main goal was a mobile robot that logically determines the right shot, moves around the table, and clears the balls on the table.
We were motivated to work on this project after seeing many physical pool-playing robot videos online. A few projects have previously worked on the pool-playing task, including our inspiration for the project, Jinger Chong and Eugenia Fang's autonomous pool-playing robot from 2023. This previous project was able to pocket a single ball from a fixed robot position. While impressive, since the robot was welded to one side of the table, it could not reposition when a good shot wasn't possible, and it did not hit more than one ball. Our contribution is a two-part system, a physics-aware shot planner, and a full table mobility and execution system that work together so that the robot can perform shot sequences.
Poolbot runs in a loop where we first gather the current table state, which is determining which balls are still on the table and their positions. Our shot planner then samples candidate shots and chooses a ball, pocket, and angle that is most robust. The mobility planner picks a good stance and trajectory around the rails, and we finally solve IK to align the cue and execute a striking trajectory. This process continues until the planner cannot find a good shot or there's repeated failures of inverse kinematics.
We originally had completely separate systems for the motion of the mobile base and motion of the arm. This led to many inverse kinematic failures, where there was not enough degrees of freedom to execute an accurate shot. Additionally, while initially combining the two systems, the arm would often reach singularity points because it was not close enough to the table. To solve these problems, we set up an inverse kinematics optimization problem that ensures the robot is near the table and as close to nominal joint positions, as well as that the Q-tip is just behind the ball, pitched slightly downward, and aligned with the chosen shot angle.
We discovered that despite the benefits of Drake's hydroelastic collisions, the hydroelastic friction was very weak despite us tuning the values, allowing the balls to seemingly go forever. We hypothesized this for two reasons. First, there is little contact area between the ball and table, as well as between the balls themselves. Second, the balls, after being hit, end up rolling with slipping, which is physically hard to model. Our solution was to add another controller to our diagram, which resists the motion of the ball with proportional force to spatial velocity. We tuned the proportionality constant, ensuring that the friction interactions were physically reasonable.
Another failure we encountered was the collision and contact models of our pool table. Unfortunately, our CAD SDS faced many compatibility issues within Drake due to complex shapes being created along surfaces from which collision models were not clearly defined. For example, the pocket displayed on screen. You'll learn that the process of creating collision models from scratch using primitives. Eventually, we were able to create invisible collision models that were relatively closely modeled to the collisions that we expected from our original CAD model.
One of our important breakthroughs was our shot planner. To determine our hit, we first sampled thousands of angles around the cue ball, checking each angle to see if the cue ball will strike a target ball into a pocket without unwanted collisions. The valid ball-pocket pairs are ranked depending on the number of angles that result in a pocketed shot. We then choose the ball with the largest number of valid angles and aim at it with a median angle.
To actually realize a chosen shot, the robot arm must be able to reach the ball. In order to do so, we discretized the space around the table into a graph of nodes and used breadth-first search to find a trajectory around the table. Our goal position is found at the heuristic that places the robot across the table from the desired pocket. From there, we solved the inverse kinematics problem as Leo described before, for a pre-shot pose. We then generate a shot trajectory keyframes by interpolating between the pre-shot pose and goal pose in task space. Finally, an inverse dynamics controller tracks the trajectory, leading to a powerful and accurate shot.
Now we present the culmination of our project, where Poolbot consistently syncs shots using our full pipeline and state machine. To evaluate shot precision, we measured the angular error between the desired solver angle and the actual ball direction. Across 10 trials, the average error was 0.0418 radians, or about 2.4 degrees, showing high shot precision. We also evaluated multi-shot performance across 10 games with 4 initialized target balls. The robot attempted 54 shots and successfully pocketed 30, for a 55.6% success rate. This rate is largely affected by inverse kinematics failures. When IK succeeds, Poolbot often pockets all 4 balls with very few attempts. While performance is strong in simulation, real-world physics such as spin and cloth effects are not modeled. If the project were extended, future work would include adding visual perception, RRT-based collision avoidance, and direct control of shot velocity.
Poolbot focuses on the game of pool, but the skills our robot uses, like reasoning about physics and planning contact-rich actions, show up in real use cases like clearing debris in rescue missions, and sets the ground for future work in this space. Thank you for watching.